Now that you know all about the pH scale, and you've studied how an acid and an alkali can give its different colours from previous topics, we can now use these ideas and look into the neutralization of dilute acids with bases, including alkalis and carbonates. But what exactly is a neutralization reaction? Well, the reaction is just the formation of a salt. And it's important to keep in mind that all neutralization reactions that happen are exothermic. This means that as the reaction happens, heat is being released to the environment. A salt forms when two substances come together, meaning the salts that form and its products depend entirely on what's being reacted, and this can happen in four ways. Firstly is mash. This is where a reactive metal, you'll usually find them in group 1 of the periodic table, will always give hydrogen gas when reacted with an acid. These can be dilute sulfuric, hydrochloric, or nitric acid. When the acids have reacted to become their salt, you must remember that hydrochloric becomes a chloride, nitric becomes a nitrate, and sulfuric becomes a sulfate. You'll see the difference in these as we work through each one and their examples. For example, magnesium and nitric acid can form a salt called magnesium nitrate and hydrogen gas. Secondly is basu. This reaction uses a base and acid to form a salt and water. When we work with bases, these are usually solids that we typically call oxides. We can say they are a base because any oxide, like bases, will not dissolve in water. And a good example of this would be copper oxide. Here, it reacts with sulfuric acid to give it salt of copper sulfate and water. Third one, which is the case of azu, if the base we choose is soluble, and it does dissolve, then we can call our base an alkali. This is usually the case with any hydroxide, and so sodium hydroxide is a good option. When this reacts with an acid, like hydrochloric acid, then the salt that's very familiar to you all forms, such as sodium chloride, as well as water, because it's a variation of basu. Lastly is cascu. As the final reaction to form a salt, a carbonate can react with a dilute acid to form carbon dioxide gas, as well as the salt and water. This is because carbonates are weak alkalis and form the same products as the bases and alkalis we just talked about. The difference is that as the reaction happens, an effervescence of carbon dioxide from the carbonate is observed in this type of reaction. Just so you know, effervescence is just a nicer word to describe bubbles. So in short, bubbles of carbon dioxide gas are produced. Calcium carbonate and hydrochloric acid are a good example, making calcium chloride, carbon dioxide, and water. So why don't we have a look at some examples and how exactly we can use what we just learned in an exam. I managed to get an old question from 2014 that, yes, it's a higher tier question, but it is easy enough if we slowly take a look at it. Question 5 says that the diagram below shows some reactions of dilute hydrochloric acid, and it asks us to give the names of each of the substances A to E. I've divided the diagram into sections. I thought this would be a useful method for you to use in an exam, as it does help keep everything a little less overwhelming, or at least it tries to. Now, taking our acid, we already know is hydrochloric acid, we can react that and get a colourless zinc chloride solution in gas A. Using what we learnt from the slide before, we notice that the metal reacting is a carbonate, such as zinc carbonate. So we can assume the reaction follows cascu. As our salt is zinc chloride, and we reacted it with a carbonate, then the gas, we can say, would be carbon dioxide. Next, we take our metal magnesium and we react it with our acid. Like before, we can say this is mash. As our metal and acid neutralize, we can say that hydrochloric makes a chloride, and that solution B is a salt of magnesium chloride. Remembering that reactive metals make hydrogen gas, we can say this is our gas C, hydrogen. For the third reaction, we see straight away that the reaction is reacting with a sodium hydroxide solution. This, as we remember, is our alkali solution, which is a base, but it can dissolve. In this case, our solution follows the Azu reaction, because as we have an acid neutralizing with an alkali, we can use the same logic as the mash salt from before, and we can say that the colourless solution D is sodium chloride. Lastly, we're told to figure out what exactly base E is. And straight away, you should be thinking of the fourth way to make a salt that hasn't already been used, and this should be Bazu. This is where we take a base and our acid to make a salt. In this case, it's different from the last two reactions because our salt is already given to us, because we're shown it's a blue copper 2 chloride solution. So this time we're told to work backwards. If we remember back to what we said about bases, we said that a good base are usually oxides. So with this in mind, we can guess that base E is copper 2 oxide. We know it's copper because we end up with this solution containing copper like we said. Looking at another example, we can use the same ideas. Even though this question does use hydrochloric acid again, it's good to recognise that nitric or sulfuric acid could be used, and so it's important to remember the naming system for them too, such as nitrate or sulfate. However, looking at a more recent question from 2019, the diagram shows 3 reactions which are used to prepare soluble salts, and we're asked a few questions about it. Firstly, we're asked to name compound A. We're shown that hydrochloric acid reacts with something to give a magnesium chloride solution. From the 4 ways we know that we can make a salt, we should recall Azu and Bazu for this question. We can't just say that compound A is magnesium, because the key word here is compound, and saying magnesium just gives an element, so straight away it can't be used. In the same way, we can't assume that it's a carbonate salt, so cascade neutralization, because as we'll see, it's used in another reaction, but we'll get to that later. Ruling these out, compound A should be an alkali or base. To use either of these would be fine, but in my case I chose to use magnesium oxide, and so I reacted my base with an acid, or reacted my acid with a base. But if you had put magnesium hydroxide, then that would have been okay too. Next, we're asked to give the names of blue solution B and gas C formed in reaction 3. As we couldn't use magnesium carbonate in reaction 2 like we said, it's safe to assume it can be used here because we have copper 2 carbonate being reacted. Because of this carbonate, we know it is a cascade neutralization. So knowing this, we can say that blue solution B is copper 2 chloride and that gas C is carbon dioxide. I should probably tell you that it's copper 2 chloride because the copper being used has a 2+ charge. If you didn't already know this, then you can easily find it in your table of common ions. Lastly, I wanted to cover something that isn't necessarily a neutralization reaction like we've covered, but balancing equations for them are almost just as important and can be easy marks in an exam if you know how to do them. Looking at reaction 1, we are asked to write a balanced symbol equation for it. It is usually a good idea to have your periodic table handy for this, and your table of common ions too. As the metal zinc is reacting with the acid, we should assume that this is a mash neutralization, and as the salt and hydrogen gas are being produced, we'd be right. Using the periodic table, we're able to find zinc, and this should be found on the top row of the widest part of the periodic table with all of the other metals. Once we have found zinc as the element Zn, we should be able to turn to the table of common ions to know that zinc has a charge of 2+. We know that the chemical formula for hydrochloric acid is HCl, because it's lovingly given to us in the question. So when these react, we end up with zinc chloride and hydrogen. You should know that from topic 1.1, when two elements come together, charges can swap with each other or cancel each other out. As chloride has a charge of -1 and zinc 2+, the charge of the chloride has no effect on it, and so the charges just swap with each other, and this is why you see the 2 here. In terms of balancing the equation, on the right side, we only have one hydrogen. Not the right side, that's the left side. But either way, side of the reactants. But then we notice that on the side of the products, we have 2 hydrogens. So as 1 times 2 gives you 2, all we need to do is put a 2 in front of the HCl, and everything is balanced out as it should be.